Good afternoon, everyone, and welcome to the second part of the B200 block series, where we delve into the details of the magnetic clutch design and associated simulation. First, some terminology to get out of the way. In the center, we've got the disk assembly comprised of the magnets, spacers, and the platters all bolted together. Alongside the outside, we have the magnetic clutch alongside the guiding rods, which allows the clutch to move vertically up and down. And the coupling between the sets of magnets is what allows the disk assembly to stay stationary whilst the lead screw is rotating such that the disk assembly can move up and down. So how did we go about simulating all of these different properties? For this, we utilize Blender and a very specific plugin called the Eletromag nodes that's available from the Blender marketplace. This was developed by electronic engineer named Sam, and essentially you can simulate the magnetic field properties and interaction between coils and current flowing through them, creating a magnetic field, and a current flowing through a wire creating a magnetic field is the same as a magnet. So for that reason we can utilize this as part of our simulation. So I'll link that down in the description below if you want to have a look at that. And you can grab a copy for only $1 for the light version, which supports the magnetic simulation. So in Blender, after pulling in all of our different CAD models from Inventor, we've got the magnets, platters, everything else as you've seen in part 1 of the video. And where all of these magnets are positioned, we went ahead and filled in all of the coils. So let's just turn that on for the different windings. And there you can see we have in total 12, so 8 along the disk assembly and 4 for the magnetic clutch, all the different simulated magnets. We can also add visualization components to this. So I focused on one set of magnets, and here you can see some of the magnetic field lines. To more readily see that, let's turn off the other bits of geometry. Let's turn off the magnets as well. And if we zoom in a little bit here, we can actually see the magnetic coupling between the magnets inside the disk assembly and then our clutch here on the outside. So note the polarity of the magnets. These two are identical on the disk assembly. And over to the left hand side, we've got the magnetic clutch as well. As part of this visualization, I've added an animation component to move the magnetic clutch magnet relative to the disk assembly. This allows us to get that relative movement and understand the behavior of the clutch. So, as mentioned, all of the polarities for the magnets are identical. So there's a total of 4 pairs for the magnetic clutch design. There's another nice rendering alongside the orientation of the magnets. And if we look at an elevation view, we can see that the magnetic clutch, if it's positioned slightly below the assembly of the disk, we've got a magnetic field interaction which will result in a net force slightly pulling this clutch in a vertical direction, so counteracting the force imparted by gravity, such that the disk will essentially float right below the disk assembly. And this is to do with the magnetic coupling, and this is also a very stable region, as if the clutch moves down a little bit below, there will be more coupling with the magnetic field, so it'll want to move up back into a stable orientation. Looking at a plan view, and this is where we move the magnet of the clutch relative to the disk assembly. We can see if the magnetic clutch is offset relative to the disk assembly. We can see the arrows pointing towards the direction of the clutch, and we will also have a component trying to pull the magnet back towards the center line of the disk assembly. So there is a component force acting on that. So we'll see a free body diagram shortly of what that looks like. Moving the magnet that it's more perpendicular, you'll see that this component becomes smaller. And if we move it all the way out towards that side, we will again see another component here trying to pull this magnet back down to this line of symmetry for the disk assembly. And because the rotation will be the same for all 4 pairs, we've got 4 times that component force acting between the different magnets. So this is an animated video that looks at it from various different angles to see the magnetic interaction. between the different magnets. So just continually moving that magnet of the clutch relative to the disk assembly. So looking at from the bottom, you can see exactly how the direction of those lights change. And keep in mind, this is not exact numbers. It's just scaled proportionally in terms of the size of the magnets to try and get an idea of the functionality thereof. And that's where the screenshots also came from. So if we consider a free body diagram, we've got the magnetic clutch here on the left-hand side, and we've got a force of gravity trying to pull down on the magnetic clutch, and then we'll have the identical force approximately coupling the magnets from the clutch, and they want to be pulled towards the disk assembly's magnets as well. And for vertical equilibrium, this will have to counteract the force of gravity. The magnetic clutch is relatively lightweight, so we don't need a lot of force to keep that magnetic clutch floating in mid-air, and it's only allowed to move vertically up and down with the guide rod, so a single degree of freedom that it's allowed to move. And as stated before, if this magnetic clutch were to be heavier or moved slightly down, it increases the coupling with the magnetic field, such that the force increases and it moves back into a stable orientation. And you'll see that in the video at the end. There is quite a large stable region for this magnetic clutch to act. So with the magnetic clutch, as the lead screw rotates, if we just have the disk assembly on that lead screw, it will want to rotate with the lead screw due to a little bit of friction between the threads, and we want to prevent that. And with the magnetic clutch, if we were to have a small relative rotation, as we've seen in the screenshots before, so we have the force from the magnetic clutch acting on the disk assembly, and we've got a small vertical component FAX working on that, and it's removed the distance d from the center point, and again it's times 4 along the perimeter of the disk assembly. Resisting that is the friction force, denoted Fr, and it's a small distance away from the center of the lead screw. For now, we just ignore all of the self-weight components and theory associated with lead screws. And the equilibrium for this just before it wants to start rotating is that the moment induced by this coupling action over here will be equal to the moment of resistance of the friction between the different threads. And because the lever arm here D is much greater than the distance arm between the lead screw and the threads, we actually need a very small force or a very small delta or rotation to actually keep that disc in place. So that allows us to have a very stable operation, and by extension we want to reduce the friction, so we want to add some lubrication between the lead screw and the assembly disc, such that it can move free. We can reduce Fr, and a smaller rotation is required such that it will keep that disk assembly in place. So in conclusion, this is what the disk assembly looks like in real life. This is a couple of photographs of the spaces and then the platters. You can see the magnets are also there with the screws being attracted to the platter over there. So as the lead screw rotates, you can see there's a bit of dynamics going on there, but essentially the magnetic clutch prevents that rotation of the assembly disc with that tangential force. And also note that the magnetic clutch is positioned down from the assembly disc by some distance, and that's due where the stable region is between the force of gravity pulling the magnetic clutch down and a force trying to pull it back up, with the coupling between these magnets and the ones in the disc assembly. And that works both for an up and down orientation, and the layout of the magnets are such that it's perfectly symmetrical, so that the weight distribution is also symmetrical, so we don't get any funny behavior as the disc moves up and down. So that's it for the clutch assembly. Let me know if you have any questions down in the description. And until next time, we'll do part 3 of this B200 video series. Cheers.